and 48 in the output. Bit number 2 of X is positioned in as bit number 3 of the output. And so on and so forth. Just by replicating some of the bits of X, we expand the input into 48 bits. The next thing we do is we compute an XOR with a round key. Sometimes people say that cryptographers only compute XORs. This is an example of that, where, well, we just do XORs in this function. And then comes the magic of DES, where actually these 48 bits are broken into 8 groups of 6 bits. 6, 7, 8. And so let me draw. And then what happens is, so each one of these wires is 6 bits. And then they go into what are called S boxes. And I'll explain the X boxes in just a minute. The X boxes are kind of the smarts of DES, S8. And then the S boxes basically map 6 bits to 4 bits. So the outputs of the S boxes are these 4 bits. They're collected. This gives us 32 bits, right? 8 groups of 4 bits gives us 32 bits. And then finally, this is fed into yet another permutation, which just maps the bits around. So for example, bit number 1 will go to bit number 9, bit number 2 will go to bit number 15, and so on. So it just permutes the 32 bits around, and that's the final 32 bits output of this F function. Okay? So by using different round keys, essentially we get different round functions, and that's how we form the 16 round functions of DES. Now, the only thing that's left to specify are these S boxes. So the S boxes literally are just functions from 6 bits to 4 bits, and they're just implemented as a lookup table, right? So describing a function from 6 bits to 4 bits basically amounts to writing the output of the function on all 2 to the 6 possible inputs. 2 to the 6 is 64, so we just have a table that literally contains 64 values, where each value is 4 bits. So here's an example. This happens to be the 5th S box. And you see that this is a table that contains 64 values, right? It's 4 by 16. So 64 values. And for example, if you want to look at the output that corresponds to 0, 1, 1, 0, 1, 1, okay, then you look at these 2 bits. This is 0, 1. And you look at these 4 bits. This is 1, 1, 0, 1. And you see that the output is 1, 0, 0, 1. The 4 bits output 1, 0, 0, 1. Okay, so the S boxes are just implemented as these tables. And now the question is, how are these S boxes chosen? How are these tables actually chosen by the designers of DES? To give you some intuitions for that, let's start with a very bad choice for S boxes. So imagine the S boxes were linear. What do I mean by that? I mean that imagine that these 6-bit inputs literally were just XORed with one another in different ways to produce the 4-bit outputs. Okay, another way of writing that is that we can write the S box as a matrix vector product. So here you have the matrix AI and the vector, the 6-bit vector X. And you can see that if we write this matrix vector product, basically we take the inner product of this vector with the input vector. Remember, these are all bits. So the 6-bit vector, inner product, another 6-bit vector, and we do that modulo 2, you realize basically what we're computing is x2 XOR x3. Right, because only position 2 and position 3 have 1s in it. And similarly, the next inner product will produce x1, x4, x4, XOR x5, and so on and so forth. Okay, so you can literally see that if the S boxes are implemented this way, then all they do is just apply the matrix A to the input vector x, which is why we say that in this case the S boxes are completely linear. Now I claim that in fact if the S boxes were linear, then DES would be totally insecure. And the reason is, if the S boxes are linear, then all that DES does is just compute XOR of various things and permute and shuffle bits around. So it's just XORs and bit permutations, which means that as a result, all of DES is just a linear function. In other words, there will be a matrix B of these dimensions. Basically, it's a matrix B that has width 832. Basically, what I would do is I would write the 64-bit message plus the 16 round keys as one long vector, right? So the message is 64 bits, and there are 16 round keys, each one is 48, and that, if you do the math, it's basically 832. Okay, so I write these guys, the keys and the message, as one long vector, and then there would be this matrix that essentially, when you compute these matrix vector products, essentially you get the different bits of the ciphertext. So there's 64 of these rows, and as a result you get 64 bits of ciphertext. Okay, so this is what it means for DES to be linear. So if you think a little bit about this, you realize the S boxes are the only nonlinear part of DES. So if the S boxes were linear, then the entire circuit is linear, and therefore it can be expressed as this matrix. Now, if that's the case, then DES would be terrible as a secure pseudo-random permutation. And let me give you a very simple example. Basically, if you take the XOR of 3 outputs of DES, well, let's think what that means. Basically, we would be looking at B times the matrix B that defines DES times one vector, XOR B times another vector, XOR B times a third vector. We can take the B out of the parentheses, so we'd be basically doing B times this vector over here, but of course K XOR K XOR K XOR K, this is just K. And so if you think about what that means, basically we just got back DES of K at the point M1 XOR M2 XOR M3. But this means that now DES has this horrible relation that can be tested, right? So basically if you XOR the output of 3 values M1, M2, and 3, you'll get the value of DES at the point M1 XOR M2 XOR M3. Now this is not a relation that's going to hold for a random function. A random function is not going to satisfy this equality, and so you get a very easy test to tell you that DES is not a random function. And in fact, it's not even, maybe you can take that as a small exercise, it's not even difficult to see that given enough input-output pairs, you can literally recover the entire secret key. Yeah, you just need 832 input-output pairs, and you'll be able to recover the entire secret key. And so if the S boxes were linear, DES would be completely insecure. It turns out, actually, even if the S boxes were close to being linear, in other words, the S boxes were linear most of the time, so maybe for 60 out of the 64 inputs, the S boxes were linear, it turns out that would also be enough to break DES, and we're going to see why later on. In particular, if you choose the S boxes at random, it turns out they'll tend to be somewhat close to linear functions. As a result, you'll be able to totally break DES. You'll just be able to recover the key in basically very little time. And so the designers of DES actually specified a number of rules they use for choosing the S boxes. And it's not surprising, the first rule is that these functions are far away from being linear. Okay, so in other words, there is no function that agrees with a large fraction of the outputs of the S box. And then there are all these other rules. For example, they're exactly 4-to-1 maps, right? So every output has exactly 4 preimages, and so on and so forth. So we understand now why they chose the S boxes the way they did. And in fact, it's all done to defeat certain attacks on DES. Okay, so that's the end of the description of DES. And then in the next 2 segments, we're going to look at the security of DES. Now that we understand how DES works, let's look at a few attacks on DES. And we're going to start with an attack called exhaustive search. So our goal here is basically that given a few input-output pairs, MICI, our goal is to find the key that maps these M's to the C's. In other words, our goal is to find the key that maps M1, M2, M3 into C1, C2, C3. And as I said, our goal is to find the key that does this mapping. The first question is, how do we know that this key is unique? And so let's do a little bit of analysis to show that, in fact, just one pair is enough to completely constrain a DES key, and that's why this question makes sense. Okay, so let's see. So we're going to prove the simple lemma. Now let's assume that DES is what's called an ideal cipher. So what is an ideal cipher? Basically, we're going to pretend like DES is made up of random invertible functions. In other words, for every key, DES implements a random invertible function. Since there are 2 to the 56 keys in DES, we're going to pretend like DES really is a collection of 2 to the 56 functions that are invertible, from 0, 1, 64 to 0, 1, 64. Okay, so of course DES is not a collection of 2 to the 56 random functions, but we can idealize the cipher and pretend that it is such a collection. Then what can we say? Then in fact, it turns out that just given one message and ciphertext, you just give me one pair, message and ciphertext, there is already only